G'day, today we're starting a new unit. Our unit is looking at the different types of chemical bonding. Today, we are introducing those types of chemical bonding and looking at something called VSEPR theory. Our lesson objective, understand how ionic, covalent, and metallic bonds form, rationalize molecular geometry using VSEPR theory. Now obviously we're going to introduce what this VSEPR theory is. So these are things I'm sure you've seen before if you're coming into this course, ionic, metallic, and covalent bonding. Good news is our understanding of the ionic and the metallic model stay pretty much the same as they already were, whereas our covalent bonding, sort of similar to how we ramped up our understanding of the electron when we're looking at the atom, our understanding of the covalent bonding is quite much more in depth, so we look into that quite a bit. Let's just look at what we've discussed previously in this video series. So we've talked about the idea of the octahedral. So just to ask a really fundamental question, why do atoms react with one another? Why does any of these types of bonding occur? Why aren't they content just to sit on their own, in their own, existing as they already are? And that is all to do with energy levels. I've said it a number of times and I will keep saying it, but all of chemistry is just things wanting to exist in low energy conformations. So they can react with each other to get into lower energy. You think about yourself, no one likes to have energy. Would you rather be jumping up and down and doing, running all over the place, or would you rather sit on the couch and just relax? You'd rather sit on the couch and relax. Same thing with atoms, I guess. They want to do the, whatever analogous is sitting on the couch for atoms. To exist in low energy conformations that are stable. What makes an atom stable? And we've said having a full outer valence shell. This is the octahedral, the idea that having 8 electrons is a stable conformation, and this is what a noble gas has. This is why our noble gases are so unreactive, and it's why the noble gases weren't discovered for such a long time, because they are so unreactive. Because a lot of the elements that were discovered by reacting them with other things. Why was it that this 8 electrons is stable? That was an analogy we looked at before. So we had our analogy of the musical scale, where the valence shell is similar to the 8 notes in the musical scale, where you've got 1, 2, 3, 4, 5, 6, 7, 8. So having 8 electrons in a valence shell is that perfect octave, very low energy, very harmonious. You can listen to that forever. Whereas if you've got something like 7 electrons, you're very close to having that 8. It's very, very much wants to find one so that it can resolve up and have that real stable conformation. Same way if you've just got 1, really wants to lose that, it's not happy existing like that, it wants to go down like that. So the closer you are to a full to a full valence shell, whether you're gaining or losing electrons to achieve that, the more reactive you are. So then we had our ones in the middle where you've got, 3 electrons, 4 electrons, 5 electrons. They're not as reactive as just having 1 electron or 7 electrons. So by having a full valence shell, that's a low energy conformation. So they want to bond chemically in order to do this, in order to fulfill this octahedral. Now we can show this with something called dot and cross diagrams, where you represent the outer shell electrons from each representative atom, dots for one atom, crosses for the other atom, so you can sort of keep track of where the electrons belong to which atom originally. Why do we only show the valence electrons? Because they're the only electrons doing anything of interest. All the inner shell electrons are still there, but they're not involved in the chemical bonding. Why would we waste our time writing all these inner shell electrons out if we don't have to? When you're doing chemistry, you've got enough on your plate already, you don't want to do extra work that you don't have to do, so we only want to show what is actually doing the phenomena that we want to discuss and talk about. So we don't show the inner shell electrons, but we know at this point in our, in our chemistry education that they're still there, we just don't have to explicitly write them all the time. And then we use square brackets to show that charge has been discharged evenly if there is a charge on an atom. Let's look first at our ionic bonding. Anions gain electrons to have a negative charge. This occurs in nonmetals. Cations lose electrons to have a positive charge, and this occurs in metals. Our periodic table, we have our metals on the left-hand side of the periodic table, our nonmetals on the right-hand side of the periodic table. Our nonmetals have an electron shell that is closer to being full than it is to be empty, so it would make more sense for them to gain electrons to complete the valence shell as opposed to lose electrons, because they would have to gain less electrons than they would have to lose in order to do that. Whereas the metals on the left-hand side, they have less electrons in their outer shell, so it's easier for them to lose, say lose 1 or 2 electrons as opposed to gaining 6 or 7 electrons. So consequently, if we gain electrons, we become a negative anion. If we lose electrons, we become a positive cation. Ionic bonds form between a strong electrostatic attraction between oppositely charged ions, something that we've been saying lots and lots, like charges repel, opposite charges attract. So if you have a positive cation, you have a negative anion, those opposite charges are going to electrostatically attract to one another. You get a very stable bond, and that's what we see. These ionic bonds are very strong and very stable. Let's show how we can represent these using diagrams. Let's look at beryllium fluoride. Looking at the periodic table, we know that beryllium is in group 2. So I'm going to write Be, don't want to use my blue, I might use my black instead. So we write Be to show that it's a beryllium atom. That's implying all the protons and neutrons and inner shell electrons that go along with the beryllium. Then we want to show the valence electrons. It's in group 2, so it has 2 valence electrons. I'm going to represent these with an X for the beryllium. We're reacting it with fluorine because we're making beryllium fluoride. So fluorine has an F to show it's a fluorine atom. 1, 2, 3, 4, 5, 6, 7 electrons in the valence shell because we know that it is in group 7. So beryllium wants to get rid of 2 electrons to have a full valence. Fluorine wants to gain 1 electron. Now in order to do this, we need 2 fluorines for this 1 beryllium because this fluorine can only take 1 of those electrons. So this tells us that beryllium fluoride is going to have a chemical formula of BeF2 because we need 2 fluorine atoms for every 1 beryllium atom in order for all those electrons to have a place to go. Our electrons can't just disappear somewhere. So we got 7 over here. So we can show these electrons moving. So 1 electron is going to be donated from the beryllium to the fluorine, and the other electron is going to be donated to the other fluorine, where the fluorine is going to take that electron. All right, so this beryllium has now lost 2 electrons, so that means it's got 2 extra protons, so it's going to become a Be2+. We've got to put this in brackets to show that that 2+ is distributed around this whole beryllium atom. Or beryllium ion now, I should say. It's now an ion. Our fluorine has now turned into a fluoride ion. So F, and I'm going to show all the electrons that it's got. So it's got its original 7, 2, 3, 4, 5, 6, 7, but it's now got 1 of the beryllium ones. So I can show which electron that is with the cross from that one. So this is why they're called dot and cross, because we can see where the electrons have come to and gone to. Come from and gone to, rather. And then we're going to have the other one, F, with its 7 original electrons, and then it's 1 electron that it's gained. It's gained 1 electron in both these cases, so it now has 1 extra electron than protons, so it has a negative charge in both cases. So we got BeF2 showing that forming over here. Let's look at another example, calcium oxide. In this case, calcium is also group 2. So it's also going to have 2 electrons in its valence shell. So it's going to be calcium 1, 2 like that. Now our oxide is group number 6. So it is going to have 6 electrons in its outermost shell for the oxygen atom. So I'll use dots because I use the crosses over here. 1, 2, 3, 4, 5, 6. In this case, the calcium wants to lose 2. The oxygen wants to gain 2, so we only need 1 of each type of atom. We can show where the electrons are going, being donated by the metal, being accepted by the non-metal, and we will form a Ca2+ to show in brackets that the charge is distributed across the whole atom, and we will have an oxygen that has now got 1, 2, 3, 4, 5, 6. But it's gained the 2, I'll just use the same color, 2x electrons from the calcium. It's got 2 extra electrons, so it's a 2-, so this is going to be calcium oxide. So using these dot and cross diagrams to show where the electrons are moving between, where our metals will lose the electrons, which button do I want? That one. And our non-metals will gain the electrons. Positive charge, negative charge, strong electrostatic attraction to form an ionic bond. What about covalent bonds? In this case, instead of one atom giving the electron and one atom receiving the electron, they are sharing it. It's a chemical bond formed by the sharing of one or more pairs of electrons between two atoms. Generally speaking, this is done in non-metals, between two non-metal atoms. Now we've got to consider the conservation of mass. We can't just pluck electrons out of nowhere, and we can't just, disappear electrons to nowhere. The electrons have to be accounted for the whole time. So the amount of electrons in the atoms that you start with need to be the amount of electrons that you finish with when you've got your molecule on the other end. I'll talk about that more when we go through an example. You can just show how the valence electrons interact in a covalent bond. Again, because those inner shell electrons, they're still there, but they're not doing anything. And we can have single, double, or triple covalent bonds. And you also need to show the electron pairs that aren't bonding. Let's explain all this through some examples. So we can use our dot and cross diagrams to show covalent bonds as well. So a covalent bond in a hydrogen. Flip over to the whiteboard. Hydrogen is in group 1. So we write H to show that it is a hydrogen atom. Let's show the 1 electron in this hydrogen atom. Now, hydrogen is one of the cases where we don't need 8 electrons in the outer shell, because that first most inner shell to be full only needs 2. Remember the 2n squared rule. Can we see that? So if n equals 1, this shell can only hold 2 electrons. So that first shell, in order to have a full valency, just needs 2 electrons. So what that means, it's already got 1, so it needs to gain 1. So in the case of H2, we have 2 hydrogen atoms. My other hydrogen atom I'm going to do with a dot, because they're dot and cross diagrams. So we can show the covalent bond by these two by having these overlap like so. One hydrogen there, another hydrogen there, and we can show the single cross and the single dot. These now have 2 electrons in its valence shell, which means the valence shell is full. We haven't created or destroyed any electrons. We started with 2, we've ended with 2, and we formed 1 covalent bond. Other ways that you can represent this, you don't need the circles, you can just do it like that, showing the bond between it. You can also show it with a line, and this is how you're going to show it most commonly, where one line represents a covalent bond, so that's the sharing of 2 electrons. So one covalent bond has 2 electrons being shared. Let's look at another example. What about oxygen? Oxygen has O2 gas. We have 1 atom with 6, it's in group 6, so we have 6 electrons in the outermost shell. Another atom has 6, 1, 2, 3, 4, 5, 6, 5, 6 like that. I'll just do my circle. So this one wants 2, this one wants 2. We have 1 electron which is on its own lonesome, another electron on its lonesome. Now, these electrons over here, they're already paired up, so they can't form covalent bonds, just these ones that don't have a pair. So we could have the oxygen form a bond with that one, oxygen form a bond with that one, and then the lone pairs that aren't pairing up are over here, like so. Again, we could draw that with a double bond. So this is the case where we've got 2 bonds being formed, our electrons that aren't being bonded off. Still need to show them, they're still in the valence shell, but they're just off on the side there. So if we look at the electron accounting, we started with 6 electrons on that, 6 electrons on that. We've started with 12 electrons here. We finished up with 2, 4, 6, 8, 10, 12 electrons over here. A very common mistake to make when you're drawing these dot and cross diagrams is you just pluck electrons out of nowhere. But if you're always checking how many electrons you've started with, how many electrons you've finished with, then it's very difficult to get wrong, because you can check it by making sure that both atoms have a full octet. So this one has 2, 4, 6, 8. This one has 2, 4, 6, 8. And then just double checking the amounts, and you know that you will be correct. So that is oxygen, that's showing a double bond there. Let's have a look at another example. HCl, hydrochloric acid. So H has 1 electron in its valence, Cl has 7. It's in group 7. So it's got 7 electrons in its valence shell. Now over here, we've been doing the same kind of atoms. Here we've got different kinds of atoms, but the same concepts still apply. This hydrogen wants to get 1 electron because it's 2 electrons in that first shell. This chlorine wants 1 electron because it has 7 electrons. So you can simply show the bond like so. They're going to form 1 bond there. We started with 1 plus 7. We started with 8 electrons here. We finished with 8 electrons here. We have a covalent bond, HCl, showing the non-bonding pairs of electrons because they are very important in the future. Let's have a look at another example. What about CO2, carbon dioxide? Now, CO2, we've now got 3 atoms as opposed to 2 atoms in all these examples. Carbon is in group number 4. So carbon has 4 electrons. I'm not going to do the actual shell anymore. You can just show it like that to save a bit of time, always saving time. Our oxygen has 6 electrons. 1, 2, 3, 4, 5, 6. Oxygen over here. 1, 2, 3, 4, 5, 6. All right, our carbon wants to make 4 bonds to have 8 in its valence. Our oxygens just want to make 2 bonds each. So what you can do is you can sort of pair them off. These 2 make a bond, these 2 make a bond, these 2 make a bond, and these 2 make a bond. So what you would end up with from here, I might just erase something to get a bit of space down here, is our carbon has now formed a double bond with this oxygen. So we've got these 2 electron pairs being shared. Our oxygen still has its non-bonding pairs. It's formed a double bond over here as well, like so. 1, 2, non-bonding pairs. And we have a CO2 molecule. Again, double check that the electrons are being accounted for. We've started off with 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons over here. In our molecule, we've got 2, 4, 6, 8, 10, 12, 14, 16 electrons over here. We haven't created or destroyed any electrons. That is our molecule CO2. Let's do one more example of ethane, C2H6. Ethane, C2H6. I'm going to make a bit of space on this board. So carbon is in group 4. That has 4 valence electrons. So 1, 2, 3, 4. C2H6, I have 2 of them. 1, 2, 3, 4. Hydrogen, that's group 1. That just has 1 electron in its valence. So what happens is we form a covalent bond between these, 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 and then a covalent bond between these, which we can write if we draw it with our lines. We end up with covalent bond there, 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 and covalent bond there. C2H6. Let's double check our electrons. We started with 2, 4, 6, 8, 10, 12, 14. We've ended up with 2, 4, 6, 8, 10, 12, 14. 14 electrons in each case. So dot and cross diagrams to show covalent bonds. There are also these things called co-ordinate bonds that also go by the name of dative covalent bonds. These are formed when one atom provides both the electrons needed for a covalent bond. So it needs to have one atom with a lone pair of electrons and a second atom having an unfilled orbital to accept the lone pair of electrons. So what can happen is you can form covalent bonds and not end up with neutral species. And you form these polyatomic ions. So ions made of more than one atom that are made from these coordinate bonds. What do I mean by that? Let's have a look at this. If you've got H2O plus H plus going to H3O plus. let's write that down here and then we'll draw some molecules. H2O plus H plus goes to H3O plus. So we're forming a coordinate bond in this reaction. Oxygen is group 6, so we have 1, 2, 3, 4, 5, 6. Hydrogen is group 1, so we have 1 in the valence. So, in order to have full valencies for all of these atoms, these are going to share, these are going to share. We end up with a water molecule that looks like this. Lone pairs there. Our hydrogen is literally no electrons. Hydrogen only has 1 electron in the valence. It's lost that, so it is just a single proton, considering it's the isotope of hydrogen with no neutrons. So, we can form a coordinate bond here where we have 1 atom with a lone pair of electrons, which is the oxygen over here. Second atom has an unfilled orbital. So even though this hydrogen doesn't have any electrons, it's still got empty orbitals there that could potentially accept or could, form the electrons could go into the empty orbital there. And that's what we show when we form the dative bond. So we have our water molecule here, like that. Now this hydrogen can form a covalent bond with the electrons from this oxygen. So the oxygen it's only the electrons from the oxygen, but it is forming a dative bond like that. So because the oxygens are coming from because the electrons are coming from the oxygen, we do an arrow towards the hydrogen, and then we still have 1 lone pair, but we end up with a single plus on this species. If you were to count up all the protons and all the electrons between all 4 of these atoms, you would find there would be 1 extra proton, so we have a +1 charge for H3O+. You can also think in terms of conservation of charge. So conservation of mass we've discussed. Conservation of charge is the same thing. If you started with a charge on this side, you need to have the same charge on that side. So we've got a +1 over here, we've got a +1 over there. Let's look at another example, the formation of an ammonium ion, NH4+. So we've got NH3 plus HCl goes to NH4 plus Cl minus. If you want to try to pause now and write the dative bond on the ammonium, you can do that now and then check when you resume now. So ammonia is group number 5. So ammonia can form 3 bonds like so. Hydrogen, group number 1. HCl, like that. So what can happen, 4, 5, 6, is that our hydrogen can essentially ionize from the HCl, so we just end up with a H+. Let's simplify this reaction a bit, just like that, the same way we showed the last one. So in the same way, we have the electron pair here, the lone pair that isn't being bonded. We have an empty orbital in our hydrogen. We can form a dative bond like so, where that empty orbital forms a covalent bond with the lone pair on the nitrogen. Again, if you were to count up all the protons and all the electrons, this would end up with a 1+ charge, charges in brackets to show that it's being spread across the whole species. One other example to consider in this coordinate bonds is this idea of aluminium chloride. Aluminium chloride, at high temps, it exists as the electron deficient molecule AlCl3. If we do an aluminium valence diagram, aluminium is in group number 3. So that means it has 3 valence electrons in its outermost shell. Al3. What am I doing? Al, 1, 2, 3. Chlorine has 7. So Cl, 1, 2, 3, 4, 5, 6, 7. Cl, 1, 2, 3, 4, 5, 6, 7. Cl, 1, 2, 3, 4, 5, 6, 7. So at low temperatures, we have this AlCl3 like that. But this is an electron deficient species because our aluminium doesn't have a full valence. It's still stable like this, but it's only got 6 electrons in its outermost shell. But at lower temperatures, so this is at higher temperatures, it exists like this. But at lower temperatures, you get 2 AlCl3 molecules forming 2 coordinate bonds to form an Al2Cl6 molecule. So if we think about our dative bonds, we need vacant orbitals and we need lone pairs of electrons. So we have a vacant orbital here. We have an aluminium that could have 2 extra electrons there to have a 4 octet. Our Cls have plenty of lone pairs. So if we had 2 of these come along with each other, what you could see is Al, let's say Cl there, Cl there, Cl there. You could form a coordinate bond where the chlorine donates, or doesn't donate, but the chlorine shares the electrons that it has to form a covalent bond here. And then this is from a second molecule of AlCl3. But then you can get a second dative bond like that. So you get this Al2Cl6 molecule at the lower temperatures. One of the things that we were saying when we were looking at our atomic model was that it's limited because it's only showing things in 2-dimensional space, but reality exists in 3-dimensional space. And we can say the same thing when we're looking at our bonding models. Up until now, we've only ever really looked at them in 2-dimensional space. But to make them more realistic, we've now got to start looking at molecules and ionic compounds and things like that in that 3-dimensional space. So we're going to look first at molecules in 3 dimension. We've been saying all along that electrons will repulse each other. So if we have electron pairs, whether they're bonded or non-bonded, around an atom in a molecule, this is going to affect the geometry that it will exist in. So we need to consider molecules in 3 dimensions. And we know that electrons repulse each other. So what this means is that they want to be as far away as possible from each other, but they're still being tied by the nucleus. So depending on how many electron pairs and bonds are around the atom in a molecule will depend on the arrangement of these. And we get these characteristic geometries. It depends on the number of pairs of electrons around the atom and whether these pairs are lone pairs or bonding pairs. And it also depends on if there's single, double, or triple bonds. So we have this thing called VSEPR theory, VSEPR theory. VSEPR theory stands for valence shell electron pair repulsion theory, which sounds very, full on when we just look at it, but if we break down each word individually, there is nothing new there. Valence shell, we know what the valence shell is. Electron pairs, we know what electron pairs are. Repulsion, we know what repulsion is. And theory, that's the theory that ties it all together. Okay, so we have all these different molecular geometries based on the repulsion of the valence shell electron pairs. The ones that we are interested in are these ones. These are the ones addressed specifically in our learning outcomes. So let's consider this in 3-dimensional space. Let's start with the simple one up here, linear. Now, what we're showing here is we're showing how many lone pairs we have down the column, where we have no lone pairs, 1 lone pair, 2 lone pair, etc. And across here, we're showing how many things are bonded to that central atom. Now, these here don't necessarily represent single bonds. They could represent double bonds or triple bonds. It's just saying how many things are bonded there. So if we have one thing that has 2 things bonded to it, but no electron pairs, the furthest this can be away from each other in 3-dimensional space is a straight line. Now, I've used balloons a lot to model in previous videos, and I'm going to do that now again. So if we have one thing bonded to 2 things, and we have 2 sections of negative space around it, the furthest these things can be away from each other is 180 degrees. So I just tie the balloons together, and they will sit in its most low stable conformation, which is a straight line. So this would be in the case of something like carbon dioxide. So carbon dioxide we drew before. We have a carbon double bonded to an oxygen, double bonded to an oxygen. We have no electron pairs. We have no lone pairs of electrons, and we have 2 things that are bonded to it. Now we have 2 double bonds. The furthest these things can be away from each other is 180 degrees, and that's shown by my balloons here. So this is the one that we have up the top. If we have 3 things bonded and no lone pairs, we get what's called a trigonal planar, which would look like this. So if you tie 3 things, the furthest these things can be away from each other is in this conformation. If you bond 4 things together, you have this tetrahedral shape. Now, depending on how many lone pairs of electrons you have, you will either get a tetrahedral, a trigonal, pyramidal, or a bent or angular. Now, we're going to go a lot more into these molecular geometries in the next video, but just to introduce it, if you have 4 things bonded, the furthest the electron pairs can be from each other is in this tetrahedral shape. Now, if you were just to draw this, such as in the case of methane, CH4, you might think that the furthest these things can get away from each other is like that, because that's the furthest you can draw them away from each other in 2-dimensional space. But in 3-dimensional space, the furthest things can get away from each other in the lowest energy conformation is this kind of arrangement. Again, we're going to go a lot more in depth in the next video. If you have 5 things and no lone pairs, you will get a trigonal bipyramidal, which looks like this one. So in this case, you've got 5 things, and this is the furthest they can be away from each other at the lowest energy. So again, just tying the balloons together, and just where they fall is showing how they will sit in the lowest energy. And the last one is when you've got 6 things with no lone pairs, you have an octahedral, like so. And that one is this one here. We've looked at that one because this is similar to our p orbitals. In fact, this is the balloon model I use for the p orbitals. But we can also show it for the molecular geometry of an octahedral, like so. So just a short introduction in that into the different kind of geometries we can have, but we're going a lot more into that in the next video. To finish off today's video, we're just going to quickly look at our 3rd type of bonding model, which is our metallic bonding model. In our metallic bonds, this is a different type of sharing of valence shell electrons. So the metallic bonding, they also share electrons in metals, as you might be able to guess from the name, but it's quite different to how it is in the covalent bond. So we have the electrostatic force of attraction between the mobile sea of delocalized electrons and the regular array of positive metal ions within a solid metal. What does that mean? I'll come back to that last bit there. So we have our metals. Our metals form cations because they will lose electrons. That's on the left-hand side of the periodic table. So if we have these atoms losing electrons, we form cations. So a cation, I'm just going to do a plus like that to show a cation. So in the metallic bonding model, the cations lose electrons, but these electrons become delocalized within themselves. So delocalized in this context means that they're free to move. So I have an electron, let's just say we have something like iron metal, where we're forming a 2+. So that means we can lose 2 electrons for this cation, we can lose 2 electrons for this cation, we can lose 2 electrons for that cation, lose 2 electrons for that cation. What these electrons do is they become delocalized and they're free to move within this lattice of metal cations. And we know that the negative and the positive attract each other, so we get a very strong bond between these delocalized electrons and this fixed lattice of cations. So cation atoms packed in a fixed tight arrangement called a lattice. The delocalized electrons are free to move between the lattice, and we get a strong electrostatic attraction, which makes metallic bonds very strong. So if I just go on my diagram a bit more, let's include this, a lattice fixed in 3-dimensional space, ordered like so. I mean, my diagram's not that ordered, but you got to imagine these are all lining up. And then all the electrons that become delocalized from these valence shells of these ions are free to move within the metallic bond, and they stabilize the negative electrons and the positive cations. It all becomes stabilized and it becomes very strongly bonded to one another. So we don't have any subscript numbers when we're doing our metals because there's only one type of atom, so a ratio isn't applicable. So unlike our ionic, where you've got something like FeCl2, because you're saying you've got 2 chlorines for every 1 ion, in this case you've only got just iron. So you don't have a ratio, so you just got your iron metal. So your metals, when you write them, don't have any subscript numbers. The strength of a metallic bond increases with the positive charge on the ions. So the more positive the charge is, if you've got a +1, a +2, or a +3, the more tightly held those cations are going to be with the sea of delocalized electrons. So the strength increases with the positive charge on the ions. It increases with the decreasing size of the metal ions. That's because the nucleus is going to be closer to those delocalized electrons. If it's closer, it's a stronger force of attraction. We talked about that in our atomic bonding model. And then finally, with the increasing number of delocalized electrons per atom. So if you've got more electrons in this delocalized C, you're going to have a stronger bond between positive cations and the negative electrons. So those three things will affect the strength of the metallic bond. And finally, you can use this model to rationalize the high melting and boiling point and the conductivity observed in metal. Rationalizing the high melting and boiling point can be done because we're saying this bond is so strong between the positive cations and the negative delocalized electrons, it will take a lot of energy to overcome that and consequently either melt or boil the metal. The conductivity is a flow of electrons, or a flow of charge, I should say. In this case, it's electrons. So if we have free moving electrons and then we put a charge on either end, and if conductivity is just how a substance can carry that charge, if these electrons are free to move, they're going to be very, very good conductors. And that finishes our first lesson on chemical bonding. What have we done today? We've described ionic bonding using the examples of sodium chloride, magnesium oxide, calcium fluoride, including the use of dot and cross diagrams. We have described, including the use of dot and cross diagrams, covalent bonding in molecules such as hydrogen, oxygen, chlorine, hydrogen, yada, 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 and coordinate dative bonding in such as in the formation of the ammonium ion and the Al2CO6 molecule. We've explained the shapes of bond and bond angles. We look at the bond angles in the next lesson, so don't worry too much about that. Molecules by using the qualitative model of electron-pair repulsion, which is our VSEPR, such as in certain examples. Now, we're going to go into this one a lot more in the next video. But then finally, we looked at the metallic bonding model and described metallic bonding in terms of positive ions surrounded by delocalized electrons. Task for this week, if you would like to consolidate your learning, here are some tasks you can undertake, one column at a time from the bottom, working the way up. Thanks for joining me. I will see you on the next video as we continue our look into the types of chemical bonding.